Okay, guys, we have seen how to solve equations with factoring, just normal factoring, completing the square, or using the quadratic formula. Now we're going to touch into solving quadratic equations that has complex solution. Before we get into that, let's find out what's a complex number or imaginary number, if they called it. That's what we're going to be doing today, just introducing to complex numbers. So first is it's important. Usually whenever you have a negative square root of a number, it's called imaginary because you can't find the square root of a negative number. And that's usually represented as I root A. So whatever value of A is, if you can find it is a constant, you know, you're able to factor out an I and you're left with root A. And if root A is a perfect square, then it would be, let's say this is 25. If the square root of 25 is 5, so you're left with 5I. Now let's find out what I actually is. So I is actually the square root of -1. That's what I is actually is. So what's happening here is that you are actually factoring a -1. So it's like saying the square root of -1 times this A all in one. And remember the rule of for square roots, the square root of AB is the same as saying the square root of A times the square root of B. So this is the same as saying the square root of -1 times the square root of A. And we know that I just introduced you to that the square root of -1 is considered I root A. So let's jump into some examples. Let's get right into business. So here we go. So let's say you're asked to simplify the square root of -25. And as I demonstrated earlier, this is the same as saying the square root of -1 times the square root of 25, which is the same as saying I root 25. And because this is a perfect square, it's the same as saying 5I. Same as saying 5I. Let's do another one. Let's say we have 3 times the square root of -80. So we have a couple factors going on here. We have 3 as a factor. We have root -1 as a factor. And we also have root 80 as a factor. And root 80 can actually be broken down into 2 factors where we can find a perfect square of one of the factors. So if in hindsight you can recognize that, it's fine. You don't have to write it out in details. I'm just doing the details so you can understand what's happening. So this is 3 root -1 root 16 root 5. And now we can evaluate our factors individually. So here we have 3 by itself. We know that the square root of -1 is I. We also know that the square root of 16 is 4. Remember, these are all factors, and then we just have root 5, leave it in exact form. So this is actually 3 times 4. We can actually multiply these two factors. So we have 12I root 5. Here we go. It's beautiful, isn't it? Okay, let's step it up a notch a little bit. Here we're going to have 2 terms that we're asked to simplify. One is a whole number, a constant, and the other one we have an imaginary number. So let's break this down. So this is actually 3 by itself, and we know that this is root 1. Let's break this down into 2 factors of 9 and 5 where we can get a perfect square. So this would actually be 3 plus I. Well, actually square root of 9 is 3 root 5. So I'm left with 3 plus 3I root 5. And that's it. We cannot combine these two because they're not like terms. This is a constant. This is imaginary. So this is just our answer right here. Let's do one more like it. So let's say we have a rational type looking number. What I would do here, because this is a common denominator for both terms in the numerator, I would separate them. Beautiful. And I'm sorry, this is all over 4. And what I would probably do here, I probably also simplify. And I know my 72 can be broken down into 2 factors of 8 and 9. But 8 can also be broken down into 4 and 2, which will give me a factor of 36. I can see right here. So this is actually 36, and 2 would be the better factor for this one. So this would be -1 times root 36 times root 2. That's what 72 would equal to. So let's break it down here. We still have a half. So this would give us 6. This would give us 6. So it would be 6 over 2. I, right? Because we have our negative square root of -1 root 2. And this can be further broken down, reduced. So the answer is -1 plus 3i root 2. Beautiful. I love working with imaginary numbers. All right, let's see what happens if we see them in terms, in the form of terms. Here you just have them as a single factor that break down. Let's say when you have to add and subtract complex numbers. Let's see how we do that. All right, so here we have the term 7 plus 4i plus 6 minus 2i, and there's nothing that we can work with here, so we can drop those parentheses. And then we can combine like terms. So here we have 2 constant terms of 6 and 7. And we have 2 imaginary terms of 4i and -2i. All right, so here we go. I can combine that. That's 13. And here this leaves me with 2i. You always want to set up your answer with the constant first and then imaginary number after, right? In order of hierarchy. Let's do one with a subtraction. Let's see. So here we have 2 terms here. We have 5 minus 8i minus 3 plus 2i. There is nothing to simplify in the parentheses, so we can get rid of that. But here we have a negative before this factor here. So this is asking to take the opposite, or you're distributing a -1 to these terms in here. So that changes the sign of everything. And now I can combine my like terms. Combine my common constants and my common imaginary numbers. So here I have 2. And I have 2 negative terms, which I'll add and keep the sign. And that's simply it for addition and subtraction. Let's see what happens when you're multiplying them now. Okay, so here we have an example of -9i times -2i. So here what I like to do, I always like to keep my common factors together. So that's -9, -2, and that's I times I, right? So here we have 18, positive 18, because when you multiply common signs, like signs, you yield a positive, and this is I squared. Now remember, I is equal to the square root of -1. So if I was to square this, right? If I was to square this, then my solution would be a -1, because remember, if you square a root, you'll end up with what's inside that root. That's a rule, right? The square root of a squared is actually a. So then the square root of -1 squared is -1. So simply putting it, you need to remember that I is equal to the negative square root of 1, and I square is actually equal to -1. So I still have to continue simplifying my problem here. So this is actually 18 times -1. So the answer here is actually -18. Let's try another one. So here we're going to step it up a notch. Here we have a factor outside, a group of terms. So this obviously is distributive property. So we have a -2i times 15, positive 50, which will give us -30i. And we have a -2i times a -3i, which actually gives us a positive 6i square. Now, if in hindsight you recognize that I square is already going to be -1, which will change the sign of that 6, go for it. But I like to take my time and do steps. So I know that this is actually 6 times -1. So my actual answer is 6i minus 6, or -6 minus 30i if I'm writing it in order of hierarchy as mentioned that. Okay, so here we go. Let's try another one. Let's step it up a notch. So here we're going to have 2 terms. And if you look at this carefully, this actually looks like a difference of 2 squares. You see, we have the same terms with opposite signs. You can recognize this as a difference of 2 squares right away. So this is actually 7 square minus 2i square. But you know, just for any type of doubters or anybody saying, you don't remember, let's do the distributive property here. Or in this case, this is a FOIL method because we have a binomial times another binomial. So this is 7 times 7, 49. And then 7 times 2i will give me positive 14i. And this is -2i times 7, which will give me negative 14i. And this is -2 times positive 2i, which will give me -4i square. All right, so here we go. We can see the 2 terms in the middle give us 0 because they have the same quantity, opposite signs. And I'm left with 49 minus 4i square. We know that I square is -1. So it's actually 49 plus 4, which is actually 53. This is beautiful. So let's see what happens if we had just cut to the chase and treat it as a difference of 2 squares. This is actually constants that can be evaluated. So this is actually 49 minus, and this is 4i square, which is also 49 minus 4 times -1. 49 minus a -4, which is actually 49 plus 4. Just taking it in steps, which is 53. And if you can go from here to here and then here, then that's fine. Remember, you have to still show some work on your test. So this is multiplying complex numbers. Let's see what it looks like for division. So when dividing complex number, it actually takes an extra step where your divisor cannot be imaginary. Your divisor cannot be imaginary. And how do I get rid of my divisor being imaginary? I have to do something called conjugate. I have to conjugate. And this is how you have to conjugate. So please conjugate. Okay? And this is how you conjugate. What you do is you multiply your numerator and your denominator by the divisor as a whole. So you see what I did? I took my denominator and I made it into 1, right? Because anything divided by itself is 1. So I multiply the top by it and the bottom by the denominator. So conjugate, in simple terms, just putting it, I'll just say multiply numerator and denominator by divisor. And the divisor in this case is also the denominator. Okay, I don't want you to think it's 2 separate things. So here we go. We know how to multiply our complex numbers. So this is actually 28i, and this is actually 49i square, which we know is a -1. So this is actually 28i divided by -49. Now remember, this is still a fraction, so you don't want to forget the cardinal rule that you must reduce. So 28i and 49, -49i, this whole thing is negative. 28 and 49 have a common factor of 7, a GCF of 7. So I can cancel out the 7s, and now I'm left with -4/7i. Isn't that beautiful? Let's do another one. Great, so we step it up a notch where we have 2 terms to work with. So I wouldn't separate these 2 to complicate stuff. I'll just leave it as is because we have a common denominator, which is good for us. So remember, we said that our divisor cannot, or denominator cannot be imaginary, so we have to conjugate, which means multiply the divisor to both the numerator and the denominator. Okay. You don't have to carry the sign. It'll be the same. So here we go. This here now we see is a distributive property. So this is actually 2i times 3 plus 8i. And it's 2i times negative 2i here. So here we're going to implement the distributive property. So this is 6i plus 16i squared over, this is actually negative 4i squared. Let's get rid of those I square factors now and see what we have. So we have 6i minus 16, right? Because that's a negative 1 times 16. And we have negative 4i squared. We know that this I squared is actually a negative 1. So now we have two negative factors, which gives us a positive. So now we have 4. Now remember, this denominator is applicable to both terms up here. So here is where we could perform our separation so we can reduce our individual fractions, because this fraction is actually two terms. The amount of terms in the denominator defines how many terms the whole fraction is. So this is a two-term fraction because there's two terms in the denominator and they share in the numerator, and they share a common denominator. So here we go. Ooh, look at that. So we know that the common factor between 6 and 4 is 2. So we're left with 3 halves. So this is 3 halves I. And we know that the GCF between 4 and 16 is 4, leaving us a factor of 4. And because of our A plus BI rule, in terms of the constant taking precedence over the imaginary number, this is negative 4 plus 3 halves I. Isn't this beautiful? Let's step it up a notch. All right, so you will see problems that look like this, and this is our divisor here, and of course we'll have to conjugate our divisor in order to operate on this problem. So here we go. We're going to multiply both the numerator and the denominator by the factor 3 plus 2i. So we have some distributive property or some FOIL to take care of here. So let's take this nice and slow. We'll start with the numerator. 4 times 3, 12. And 4 times positive 2i is positive 8i. Then negative 3i times 3, it'd be negative 9i. And negative 3 times positive 2i is positive 6. Negative 6i squared. Okay. Taking my time. So here, oh no, apologies guys. Please erase this from your memory. Conjugation still takes place, but when we're working with terms in our divisor, we have to do opposite signs. When working with terms in our divisor, when we're conjugating, we have to do opposite signs. So this is actually 3 minus 2i over 3 minus 2i. My humblest apologies to you. I'm only human. All right. So here we go. I'm going to restart this process. I'm going to do my FOIL. 4 times 3, 12. 4 times negative 2i is negative 8i. Negative 3 times 3i times 3 is negative 9i, and negative 3 times negative 3i times negative 2i is positive 6i squared. Here we can see clearly it's a difference of 2 squares, so we can cut to the chase, and you can label that 3 squared minus 2i all squared, and then we'll simplify that in a few. So let's work on simplifying our numerator. So here we have 12, and then we have the like terms of negative 8i and negative 9i, which will give us negative 17i. And then we know this is 6i squared, which I squared is negative 1, so this is now a negative 6 over 9, right? Minus, this is 4i squared. All right, let's get down to simplifying. So we have a common terms here, 12 and negative 6, which will give us 6. minus 17i. And then at the bottom here, we have 9 and negative 4, right? In parent 9 minus negative 4, which will give you positive 4. So it's actually 9 plus 4, which we have is 13. So our solution here, we can leave it as is, or you can separate the terms. And that's all there is to it. Sorry about that error initially. If you have any questions or concerns, you know how to reach me.